Hello, we are Lambent Hygienics, and today we are presenting a short PowerPoint on the advantages of the direct ultraviolet antiviral system. Before we discuss the direct UV antiviral system, let's review the traditional antiviral measures in use. They're divided into active measures and passive measures. Active measures require individuals to perform some action. To be most effective, every individual needs to perform the action. Thus the term compliance. Passive measures require no action from the individual because passive measures are going on in the background. So active measures include periodic surface wipe down, typically with some sort of chemical disinfectant. To be effective, it needs to cover all surfaces, and that makes it labor intensive. Hand washing really doesn't need an explanation. Social distancing, we're all familiar with the 6-foot rule. Droplets from the mouth or nose are supposed to settle in that distance. However, there is evidence that aerosolized virus can travel further and linger much longer in the air in an enclosed space. And it also relies upon compliance. Mask wearing or face covering will block exhaled virus and prevent a portion of airborne virus from being inhaled. The effectiveness is dependent upon the mask design and fit. And of course, you can't eat or drink while wearing a mask, so they're not going to be as effective in a restaurant setting. Masks also heavily rely upon compliance. Passive measures include induct UV systems, which have germicidal UV lamps placed inside the HVAC system. There's no occupant exposure and there's no surface disinfection. But keep in mind, most induct systems have been sized to prevent mold buildup on the cooling coils of the HVAC system, not to disinfect the air passing through them. Since this air velocity in the duct is quite high, the UV lamps must be properly sized, meaning quite a few of them and a lot of power to be effective in inactivating airborne viruses. Upper air or indirect UV systems have germicidal UV lamps mounted at the top of the room, parallel to the floor. The systems are least effective with poor air movement, since the virus needs to move to the top of the room where UV exposure can occur. There is no direct occupant exposure. They typically have louvers on them to direct the UV out parallel to the floor, but there's no surface disinfection. Finally, there's offline UV systems, and these deploy a multi-directional bank of germicidal UV lamps that activate virus in both the air and on exposed surfaces. They can be automated, it can be a little robot system going around in the room, but they can't be used while the space is occupied. And obviously, once the lamps are turned off and people return to the space, the system offers less and less protection against viral transmission. The idea behind the Lambent Hygienics approach. We know that outdoor transmission of COVID-19 is much less common than in indoor spaces because of sunlight and fresh air. Sunlight contains a portion of UVB light that is virucidal, and there's unlimited air to dilute and carry the virus away. Our aim is to make interior spaces like the outdoors by adding carefully controlled amounts of germicidal UV light and optimizing air movement and exchange. This presentation will focus on the UV element in prevention of the spread of virus. Why is our system superior? Well, most importantly, it inactivates virus circulating in the air and on surfaces while the space is occupied. Other antiviral systems can't do that. Second, it runs constantly. Third, while no antiviral system can guarantee 100% virus inactivation, our system greatly reduces the exposure load. There is research showing that the odds of acquiring an infection is virus concentration or dose dependent. which means the less virus breathed in, the less likely an infection occurring. There is also a theory that the severity of an infection is dose dependent. Either way, the less virus in the air, the better, and our system will achieve that. Finally, there is the potential for creating ad hoc viral vaccines, and we will speak about this a little bit later in the presentation. Here's an example in a restaurant setting. This simplified example does not show any existing HVAC system influence. So germicidal lamps are mounted on the ceiling, pointed downward. Like all light, UV propagation downward follows the inverse square law, so the intensity decreases the further from the source. So it's strong up here top and slowly diminishes as it gets closer to the floor. And we calibrate the UV lamps so that the short-term occupants, meaning the restaurant customers here having a meal, do not exceed the NIOSH standard for germicidal UV exposure. The longer-term occupants, such as this employee, who would be the server, don personal protective equipment, such as a hat, long sleeves, and protective eyewear. The overhead ceiling fan is placed in reverse so that it is drawing air up into the region of high UV flux, where the virus is quickly inactivated. The air that's been exposed to the high UV flux then circulates back down, so we have this circular air pattern. In a moment, this slide will show a simulation of how viral particles shed from a person in the center of a poorly ventilated room progress. Particles move in random directions and velocities dependent upon the air currents. The simulation takes place over an accelerated 100-minute period. The room on the left has no overhead UV. The room on the right has direct germicidal UV. As you can see, the room with the UV remains nearly virus-free. Now that we've covered the various types of germicidal UV installations, it's important to understand how UV actually inactivates a virus, or for that matter, other microorganisms. There is a specific range of wavelengths of light within the larger ultraviolet spectrum that are resonant with portions of the genetic code material. This spectral region is known as germicidal UVB, which is occurring in sunlight, or UVC, which is occurring in germicidal UV lamps. When a wave of energy strikes matter, three things can happen. Some of the energy can be transmitted, some of the energy can be reflected, and some of it can be absorbed. So when the genetic material, in the case of SARS-CoV-2, its single-stranded RNA, is struck by a photon in the subject wavelength, the energy of the photon is absorbed and the genetic code is corrupted. This ultimately prevents the virus from being able to be reproduced. So at this point, the virus is considered to be inactivated. And we use the word inactivated instead of killed because a virus is not considered to have ever been alive, since it depends on the cellular mechanisms of other organisms to be reproduced. The SARS-CoV-2 virus is very susceptible to UV. And different biological pathogens have varying sensitivities to UV, which depends upon several things. The complexity of their genetic code. So the larger the genome, the more susceptible. SARS-CoV-2 has a fairly large genome for a virus, so making it more susceptible. The composition of the genome, chemical composition. RNA is more unstable than DNA, and the SARS-CoV-2 virus has a genome comprised of single-stranded RNA. And then finally, the presence of protective materials surrounding the genome, proteins, lipids, and in the case of SARS-CoV-2, doesn't have any of those structures, so it's fairly bare and unprotected. It's making it more susceptible. And I want to point out that other types of microbiological pathogens, such as bacteria and fungi, they have intercellular mechanisms to repair damage to their genetic code. So if it gets corrupted once, there's a good chance that it will get repaired. And so that's why they generally require more UV energy to inactivate them or kill them. And special cells, bacteria and fungi, can form spores. They've been especially hardened towards the environment, and that makes them even harder to inactivate, so they require even a larger dose. What are the public health implications of the direct UV system? Well, it fundamentally changes the relationship of protection against infectious pathogens in that the protection is automatic. It doesn't require individuals to change their behavior. And it doesn't rely upon compliance. Think of the trillions of dollars in lives lost from the pandemic. How much would it cost to retrofit public spaces? And keep in mind, many existing lighting fixtures are compatible with the UV lamps. It would be a small fraction of what the United States government has already spent. And finally, it provides protection into the future, available at the flip of a switch. It actually could be the end of pandemics. Earlier, I mentioned the concept of ad hoc vaccines. And in order to understand how that works, let's first quickly review the background of how vaccines work. A well-known method of creating an active vaccine is to expose a person to a weakened or inactivated version of the subject biological pathogens. Heat energy or chemical means can be used to inactivate the pathogen. The immune system learns the characteristics of the subject pathogen from the fragments of the pathogen, but does not acquire the disease because it's inactivated before inoculation. At a later time, if the person is exposed to the same or similar pathogen, the immune system is quick to recognize it and mount a timely response. So how could an ad hoc vaccine work? Well, we'll refer to it as a passive vaccination potential. So this is how it might hypothetically work with the SARS-CoV-2 virus. When an infected person sheds viral particles into a direct UV environment, either from speaking or breathing, these particles are eventually hit by energetic photons, the germicidal UV, and that corrupts their genetic code. Susceptible people within the shared space inadvertently inhale or transfer by touch those deactivated viral particles into their body. And those viral particles will still have the active spike protein on their surface, so they'll bind with the receptors on the target cells as they would normally do with an infection. Once an inactivated virus is inside its target cell, viral reproduction is inhibited because their genetic code has been corrupted by the germicidal UV. But the spike protein and other viral elements are still present, so the immune system can still mount a response to those elements. The question remains if the immune response to the passive vaccination would be strong enough to create a lasting immunity. This is an open question not only for passive vaccination, but for active vaccination. For all of the vaccines in development right now, they're trying to answer that question. So for now, just consider this a potential bonus than rather the focus of the direct UV technology. Naturally, there are some frequently asked questions about the direct UV system. So the first question is an ultraviolet light potentially dangerous? How can people be in the same space as this kind of light? The answer is there is an industrial safety standard created, the NIOSH standard referred to earlier, for work settings where incident UV is likely to be encountered, and the maximum daily exposure limits have been established. The answer 2, we live our lives in the presence of sunlight, which contains UV, and even a small amount in the germicidally active UV. Most of us barely think twice about going outdoors in the sunlight, especially for shorter periods of time, like say an hour, the amount of time that you would sit at a table in a restaurant. Answer number 3, we weigh the UV risks against the risk of SARS-CoV-2 to ourselves or our family members if we live with, if we ourselves were to become infected. And finally, there is effective personal protective equipment available for UV if we feel extra protection is warranted or wanted. Next question. Okay, so you're limiting the amount of UV to make it safe, but then isn't it too small to be effective for its germicidal effect? The first answer is we know from studies in the presence of even a small amount of germicidally effective UV in sunlight that the SARS-CoV-2 virus has a mere 90 seconds half-life. We consider this to be a useful effect. And then the next answer, the SARS-CoV virus is particularly susceptible because it's single-stranded RNA type virus. Next question. Okay, so you're limiting the amount of UV and it's effective, but let's say my employees work all day in this environment and don't want the equivalent risks and effects of being in the sun all day long. Answer. People expected to spend extended periods of time in the protected spaces should deploy UV-specific personal protective equipment, the same as a person with fair skin going to the beach for the day, such as a wide brim hat, eye protection, and long sleeves. Answer 2. Another thing to keep in mind is that indoor temperatures can still be controlled, so we're not talking about being exposed to the heat of the sun, just the UV. Answer number 3. The germicidal wavelengths in sunlight, generally classified as UVB, actually penetrate more deeply into the layers of the skin than the shorter wavelength UVC than our system depends upon. One more question. The 90-second half-life doesn't mean I'm completely protected, though. If I'm talking to someone and the virus particles they express reach me in under a minute and a half, I'm still being exposed to more than half of them, right? Answer. That is correct, but the thing to keep in mind is the deployment of these measures makes the difference between being infected by a person that you spoke to and the case of you merely walked through a room in the evening that had contained an infected person that morning. Remember the side-by-side room simulation. Answer 2, the dramatic difference between these two levels of spread make the difference between a locally isolated case and a pandemic. This would keep R naught less than 1. Answer 3, this renders contact tracing viable. So the question to the infected would be, who did you speak with in the last week, rather than who were all the people that got onto your subway train after you last week.